All right, now let's have a look at the final question for ideal gases, and that is question 9. So I typed this example out, but it's actually from a tutorial. And it says a gas has the following composition, okay? It's got 40% hydrogen, 20% methane, 15% carbon dioxide, and 25% nitrogen. I apologize for the lack of subscripts here, but I think you understand what I'm trying to say. Okay, and this gas flows in a 200 millimeter diameter pipe at 5.22 sm cubed per second. Now, I remember when I was studying, I was super confused about what this whole S and N means. Okay, in the semester test 1 preparation, I also discussed ideal gases there. But I told you, don't freak out, right? Anytime you see S or you see N when you're dealing with gases, just remember that it's a shortcut for specifying what the temperature and pressure is. So if you see S, it's telling you that you are at standard conditions. It's just a shorter way of saying that the temperature is 298 Kelvin and the pressure is 101.325 kPa. And if you see normal cubic meters per second, or nm cubed per second, that is a shortcut for saying that the temperature is 273 Kelvin. That's a shortcut for saying that the temperature is 273 Kelvin and the pressure is 100 kPa. That's the only thing that really matters here. Okay, so don't freak out when you see this sm cubed. I'm just telling you that it's standard and that the temperature and pressure is predefined. Okay. And I'll give you a bit more of an idea about why we use this, but that's at the end of the video. Let's not overcomplicate things for now. Okay. Then they say to me, the actual PNT in the pipe is 300 kPa and 21 degrees Fahrenheit. Oh, that's not a Fahrenheit, that's a Celsius. Okay. And 21 degrees Celsius. What is the linear velocity of the gas? So let's start off. A good way to solve the question is to always start from what you want to know and ask yourself what pieces of information you need in order to get to the final answer that you started off with. Okay, so the first thing I see is they're asking me for what is the linear velocity of the gas. So if you remember, linear velocity is a pretty straightforward calculation. Linear velocity is equal to your volumetric flow rate in cubic meters per second if you're dealing with SI units, divided by the area of the pipe. So do you agree finding the area of the pipe is pretty easy, right? Area equals pi over 4 times diameter squared, and I've already been given that the diameter is 200 millimeters. So I'm not too concerned about that, right? If I'm looking for the linear velocity, I can work out the area of the pipe, but I don't know the volumetric flow. Okay? If I wanted to find the volumetric flow, I can say, oh, well, let me try using the ideal gas law. PV equals nRT. Okay? So I know the actual temperature and pressure of this gas was 300 kPa. I know the actual temperature was 21 degrees Celsius. I know what the ideal gas constant is, but you see the problem I run into here. I cannot get the volumetric flow because I do not know the number of moles. So now we've hit a snag, we've hit a dead end. I don't know how many moles of gas we have in this pipe. But that's why they give us the information at the beginning of the question. They say a gas has this composition and it's flowing through this size pipe at 5.22 standard cubes per second. So let's just have a look at that quickly, right? I'm just going to write it down here. I'm going to say, but at standard conditions, which is T equals 298 Kelvin, and at P equals 101.325 kPa, I know that my volume was 5.22 cubic meters per second. So if I put this into the ideal gas law, PV equals nRT, then I know what my pressure is, and I know what my temperature is because it's at standard conditions. I know what the ideal gas constant is, and I also know what the volumetric flow rate is with a little dot on top because it's a flow rate per unit time. And my only unknown is my number of moles. And do you agree, if I know the number of moles at this temperature and this pressure, then even if you move to a different pressure and a different temperature, like over here, you move to 21 degrees Celsius and 300 kPa, even if I move to a different temperature, the number of moles of gas in that pipe is not going to change. I agree, right? If I have the amount of gas flowing through a pipe and I've got it as a volumetric flow rate, and then I change the temperature or the pressure, do you agree that gas could compress and now my volumetric flow rate changes, right? My volumetric flow rate can change, my pressure changes, my temperature changes. But the number of particles, the number of moles of gas in that pipe will not change between a different temperature and pressure. And that is the number one thing you need to realize. So I'm going to write it down here. Once you make this realization, the rest of the question is easy. So I'm going to say the number of moles at P equals, what was the pressure up here? Here, standard conditions, right? So at P equals 101.3 and T equals 298 Kelvin, okay? That is exactly the same as the number of moles, pressure equals 300 kPa, and temperature equals 21 degrees Celsius. The number of moles between these two situations is exactly the same. And once you've made that realization, we are good to go. So let's see if we can go all the way back to the top and see if we can work out from here, from this equation, what the molar flow rate is. Okay. So I'm going to say here, at standard conditions, okay, I know that PV equals nRT. Okay, my pressure was 101.325 kPa. My volume was 5.22 cubic meters per second. The reason I don't need to include the standard in here is because standard is already taken into account by the pressure and the temperature. But you can write it in if you want to. Okay, number of moles, R is 8.3145, and my temperature was 298 Kelvin. So if I solve this, then the number of moles comes out to be 0.213. And remember, your answer is going to be in kilomoles per second. So of course, this is going to be a volumetric flow rate, and this is going to be a molar flow rate. So I put a dot on top to indicate that it's per unit time. Remember, if you're using the normal ideal gas law, this is just cubic meters, not cubic meters per second. Similarly, this N represents kilomoles, not kilomoles per second. So that's why I put the dot on top, just to indicate dimensional consistency. I've divided both sides by seconds. All right. So if I know that there are 0.213 kilomoles per second at standard conditions, then I can say at P equals 300 kPa and T equals 21 degrees C. Let's add a line there. Okay, at these conditions, I know that N is still equal to 0.213 kilomoles per second. And once you've shown the examiner that you understand that, you are basically done with the question. So now I can say PV equals nRT. My pressure is 300 kilopascal. My volume is unknown. Okay, I'm going to put a dot on top. Number of moles is 0.213 kilomoles per second. And I'll also add the dot on top here and the dot on top here. R is 8.3145. And my temperature, remember, the Kelvin police will find you. This is 294 Kelvin. So my volumetric flow rate comes out to be, and that's 1.736. And that's cubic meters per second. That's my volumetric flow rate. But remember, finding the volumetric flow rate was not the end of the question. So I always just like to keep my answers in boxes so you can follow each stage. So here I'm calculating for standard conditions. Here I'm calculating for the new conditions. Okay. And finally, I want to calculate my linear velocity. Okay, that's the final step. So for my linear velocity, that's going to equal to the volumetric flow rate divided by the area of the pipe. And remember, I've got the volumetric flow rate at the desired pressure and temperature. So at this pressure and temperature, my volumetric flow rate was 1.736, and the area of the pipe is pi over 4 multiplied by the diameter. Remember, it's 200 millimeters, which is 0.2 meters squared. Okay? And if I put that into my calculator, and that gives me 55.24 meters per second as my linear velocity. And remember, this is the linear velocity at the specified temperature and pressure. Okay, at 300 kPa and 21 degrees Celsius. So this is my linear velocity. Now, I just want to have a quick chat with you so you can appreciate where this is coming from, right? Why do we even have standard and normal temperature and pressure? So let's say I installed, let's say I installed some kind of analyzer. This is a pipeline. And I installed some kind of flow meter, okay, a flow transmitter to see what the gas flow rate in a pipeline is, right? This flow meter cannot physically count how many moles of gas are in the pipe. It's just not a technology we're able to do. But your flow transmitter will report back to you perhaps a cubic meters per second, a volumetric flow rate. But of course, to me, yeah, having a volumetric flow rate is nice, but remember, your volume is always going to be temperature and pressure dependent. So what I can do is, I can say to the flow transmitter, okay, you know the ideal gas law, and you are telling me what the volume is at this temperature and this pressure. But anytime I have an upset in my chemical process, let's say my temperature gets too high or my pressure gets too low, or the pressure gets too high and the temperature gets too high, then do you agree my volume is always going to be varying, right? Because as my temperature and pressure change, my volume is also going to change. And I'm never going to have a standard or a reliable source of data, because my volume graph is going to look like this all the time, every time my pressure and temperature changes. So instead, I can tell the flow meter, all right, once you calculate the volume for me, can you please convert that volume into a volume at standard temperature and pressure? And that way, you've always got a continuous basis, right? You've got a fixed temperature and pressure. Your temperature and pressure is always fixed. And so the volume that you read is going to be a lot more reliable and more accurate and more stable compared to a process where the pressure and temperature is continuously changing. Because remember, chemical plants are running often 24 hours a day. So you are always going to have some degree of variability in your process. And if you take that into account in your measurements, you're going to have a very noisy measurement source, and you're not going to be able to conclude anything from it. And that's why it's easier for me to just report that the gas flow rate is 21 standard cubic meters. And then everyone knows that we are all using the same temperature and pressure, and that it's my volume that is actually varying and not the temperature and pressure. Okay, so I hope that was helpful. Thank you for watching. Now we can move on to the next section.